So we have our dissection of the problem into smaller ones, but we still want to combine them. And for that, we had the problem in the beginning. We don't know how to combine stuff because we don't know how it looks like at the boundary, but now we have the portals for that. So what we want to compute in every square, that's still not so clear because we still don't know how to use these portals. And that we want to define now, because for all of these smaller squares, we want to find so-called well-behaved tours. And let's figure out what a well-behaved tour is. So if we have our instance here, we have the dissection, and we have our houses. Then what we want to find is some tour, so we have to define what are the properties this tour can have. For example, this is a tour, but for obvious reasons, this is not a tour that we want to find. The first reason is it doesn't visit all the houses. So, of course, a well-behaved tour has to visit all houses. Like this. And then we have all these portals, so it involves all houses, but not all of the portals, only a subset of them. But there are still two things that I don't like too much about this tour. Can you figure out what? Well, the first one is down here. We cross this basic dissection line, but not at a portal. And that's not something we should do. So our further restriction is no edge of the tour can cross a line of the basic dissection. Instead, we would have to use one of those two portals here and reroute the one. Well, the next thing is the optimum tour is always crossing free. So I would like to find a tour that's also crossing free. That gives me the question, what about this guy here? We have this portal, and we enter it twice and leave it twice. Is this a crossing for us, or is it not? The answer is, I don't know, because it depends on where do you leave again. So we can define what a crossing is. If we have two edges that just cross each other, that obviously is a crossing. But if we go through a portal, then it depends which way. If we go straight through it with both, then this is a crossing. But if we leave on the same side, then this is not a crossing, because if we just move this very little bit away from the portal, then those two paths don't cross anymore. So here it depends. Does my tour go through it like this? Or does it go through it like this? Well, the thing is, it doesn't really matter. If I go through it like this, then I can just take the subtour here and revert it. And then instead of going this way, I go the other side. And then I don't have a crossing anymore. So at the portals, it totally doesn't matter at all. And only at the edges in between, we have to take care that we don't have a crossing. There's one more thing. I want one more restriction. And that is that no portal is visited more than twice. So here we visit this portal twice, because twice we go in and out again. If we visit it a third time, then we can quickly change the solution and get one that doesn't cost more, but is still valid, where we only visit it twice. And in the homework assignment, I want you to find out how to do that. So that means as long as we find a well-behaved tour that visited all of them only twice, we still can find a very good approximation. So we can restrict our solution space to only those well-behaved tours where we visit every portal at most twice. Now, how do we want to compute the well-behaved tour? So these are the restrictions I want to have on the tour. This is what we want to find. And then we have to show that there is some well-behaved tour that is within a factor of 1 plus epsilon at most away from the optimum, and that we can find the best well-behaved tour with our program. And then we have to show that our algorithm has a running time that's polynomial in n, not necessarily in epsilon. And the runtime we want to show is the following. We can find an optimal well-behaved tour in 2 to the order of m time. If you remember, m was in the order of log n divided by epsilon. With the logarithm rules, 2 to the log n is just n, so this is n to the order of 1 over epsilon. So this is polynomial in n, but not polynomial in 1 over epsilon. And the way we want to do this is with a dynamic program. The dynamic program finds for every square an optimal solution with some more restrictions. And this dynamic program computes for every square in the dissection tree an optimal tour with some more restrictions. So actually it computes many optimal tours, because when we are down here in the square, we don't know yet where it will have to connect to the next ones. But we can guess which of the portals we have to use. So if for all combinations of portals we can use, we found the optimum one, then we can combine these somehow to get a well-behaved tour for the larger one. That's the basic idea. It's of course not so easy, because that sounds like a lot and we have to give a bound on that we do in the next part. But that's the basic idea of this dynamic program. And that way we can efficiently propagate bottom up through the dissection tree these solutions to get one for the larger square. And in the next part we want to figure out how to do that.